We consider the change as perpendicular to the motion, which gives us the time scale that energy is being given to the system so that it relaxes to an equilibrium configuration. Let's consider now the changes in the direction of motion, the parallel one, that's going to behave like a drag. So an object with mass m is moving then through this field of small objects, each of them with mass little m. We calculated what a single collision will do to the perpendicular component of the velocity and to the parallel component of the velocity. The effect on perpendicular velocities zeroes out linearly and is only felt quadratically as a random walk, but the effect on the parallel will accumulate linearly. And you can imagine that's because of the symmetry that you have in the perpendicular component, but the lack of symmetry that you have on the parallel component. We can calculate the number of collisions in a time interval dt, which we calculated in the previous video. FV/dv is the distribution of stars within a unit volume with velocity between v and v plus dv. And the rest here, 2 pi b dB vdt, is the volume of this cylinder here with dB. Integrating over impact parameter b, we would find the number of collisions. Now for the energy relaxation in the perpendicular direction, we checked the behavior of the modulus of delta v perpendicular squared. But for the momentum removal in the parallel direction, we're going to examine delta v vectorial in the parallel direction. So the momentum change is going to be given by this distribution multiplied by delta v parallel and integrated. The integral here is done in b and v, but is keeping dt so that the left-hand side is infinitesimal. So if we divide that by dt, we will have the drag force, which is then given by this expression. We can substitute now the expression that we had for delta v parallel, leading to this expression. And again, we can rearrange this integral as first an integral in b and then an integral in v. So that's the integral in b here in impact parameter. We can solve this integral, throw this on sin pi or Wolfram alpha, and this is what you find. Which once you substitute the limits here, Bmax and Bmin on the b, this is what you get. We can approximate now the Bmax is much, much bigger than Bmin. Now substitute the definition of the Coulomb logarithm, and that's the expression that we have in the end. So a simpler integral than before. The mid integral gives you simply b square minimum times the Coulomb logarithm, leading to this expression and for the drag force, where we substituted the expression for Bmin. This was the expression found by Chandrasekhar. What we're going to do next are particular cases and approximations, but this is the general expression. We still have this integral here left, which is an integral of the vector v in Vm, the mass of the smaller objects. So let's substitute the vector v by Vm minus V big M, and then integrating V little m, using also that the stars are distributed in a Maxwell-Boltzmann distribution. That leads to a horrible integral, but the result is this, is an error function and a dependency then on V cubed. Now in this expression here, x is V over the square root of 2 times the dispersion of velocities that comes from the Maxwell-Boltzmann distribution. And this is the definition of the error function. Now some of the properties of the error function is that at x equals 0, it is equal to 0. At infinity, it's equal to 1. And for x much, much less than 1, it goes linearly with x. And for x much, much bigger than 1, it goes to 1 following this expression. We're mostly going to use values of x between 0 and 3 and center at around 1 because x here is v over the velocity dispersion. So we can check here how this expression will behave. Let's plot the function. So let's define here this parenthesis, which is the error function minus 2x over square root of pi times the exponential minus x squared. So there we go. That's the behavior of the error function. As I said, as 0 is equal to 0, x going to infinity is equal to 1. And most of the values that we are interested in are between this range here from 0 to 3. But the function as we have actually is this expression divided by v cubed. So let's see how this behaves if we divide this by x cubed. Now that's the function that appears in the drag force. It quickly goes to 0 at large x because of this 1 over x cubed. So now that we know how this function behaves, let's go back to the drag force. Let's write rho equal to n naught times m for the density of smaller objects. And considering also big M much, much bigger than little m, so that we can approximate the sum here by simply big M. Then we have this expression for the dynamical friction. As you see here, it depends on the velocity here on the right-hand side and the differential of the velocity on the left-hand side. There's a minus sign. So we can write this compactly if we define everything in here as a friction time. So the friction time is defined by this expression. Okay, that's not the most enlightening, but let's consider a limiting case so that we can see what value of the friction time we get. If we go back to the figure, we have here that this value of the function in parentheses, and in the range of interest here, it is about a half. So we can approximate this by 2. It's going to cut to this 4. So I have this expression for the friction time. Let's consider now circular orbits. So the v is equal to omega r. And let's, for the sake of the argument, consider a Keplerian orbit where omega squared is equal to gmg, where mg is the mass of the galaxy, over r cubed. So that's the expression I get here. Now, if we approximate to the mass of the galaxy by homogeneous distribution density, 4 pi rho r cubed over 3, then this is what we have for the friction time. We cancel the rho's, and we have something that depends on the radial position, the velocity, and the mass of the object, and the Coulomb logarithm. Now, the approximations done here are crude, but we did find a factor of only 2/3 in front of the scalings, which is not far from 1. So we can say that up to a factor unity, the scaling is actually the value of the friction time. So if you have typical values of the distance, the circular velocity, and the mass of an object, and the Coulomb logarithm, that's the expression that we get then for the friction time. Now for the galaxy, the Coulomb logarithm is about 10. So that's going to cut to the 10 to the 11. I'm going to give something of the order 10 to the 10. So we can say that for a cloud of 10 to the 6 solar masses, one of these molecular clouds here is orbiting in the galaxy. As it orbits, it pulls stars in its wake, and this wake of stars is going to exert a drag in it, and this drag force is going to make the orbit decay within a time scale of about 10 billion years, which is about the age of the galaxy.